Welcome back to 600x. Today I want to talk about pi. Oh, wait a minute. Not that pi, this pi. For thousands of years, people have known that there is a constant called pi since the 18th century, such that the circumference of a circle is equal to pi times the diameter, and the area of a circle is equal to pi r squared. What they didn't know was what value should pi actually have. One of the earliest estimates of pi can be found in the Egyptian Rhind papyrus, circa 1650 BC. It estimated pi to be 4 times 8 over 9 squared, which, if you evaluate it, works out to roughly 3.16. Not quite right, but a pretty good estimate for the time frame. More than 1,000 years later, the Old Testament implied a different value for pi when giving the specifications of one of King Solomon's construction projects, as described here. And he made a molten sea 10 cubits from the one brim to the other. It was round all about, and his height was 5 cubits, and a line of 30 cubits did compass it round about. Well, if you parse this and solve for pi, what you see it saying is that 2 times 5 times pi is equal to 30. Well, since we know that 2 times 5 is 10, we can solve for pi and say that pi equals 3. Not quite as good as the Rhind papyrus. Somewhat later, Archimedes of Syracuse derived upper and lower bounds in the value of pi by using a high-degree polygon to approximate a circular shape. Using a polygon with 96 sides, he concluded that pi was somewhere between 223 over 71 and 22 over 7. Giving upper and lower bounds was a rather sophisticated approach for the time, somewhere around maybe 250 BC. Also, if we take pi as the average of this and this, we come up with the value of 3.1418. Really strikingly good for the time. An error of about 0.0002. We now have a long gap. We go from 250 BC to the 18th century, when the French mathematicians Buffon and Laplace proposed using a stochastic simulation based on dropping needles to estimate the value of pi. Think about inscribing a circle in a square, where the square has sides of length 2, which means that the radius of the circle is of length 1. By the definition of pi, we know that the area is equal to pi r squared. If r is 1, that tells us that the area is equal to pi. So if we could find the area of this circle, we would know the value of pi. Buffon suggested that he could estimate the area of the circle by dropping a large number of needles, which he argued would follow a random path as they fell. And if he dropped them in the vicinity of the square, some would fall out here, and he could ignore those. Some would fall in the square, but not in the circle, and some would fall in the circle itself. Now, if we know that the locations of the needles are truly random, we can conclude the following: that the ratio of the number of needles that land in the circle to the number of needles that land in the square should be exactly the same as the ratio of the area of the circle to the area of the square. Now we can take this equation and solve for the area of the circle and say that the area of the circle is going to be equal to the area of the square times the needles in the circle divided by the needles in the square. Just simple algebra. Now remember, we concluded that the area of the circle was exactly pi, so in fact, we can now compute pi by looking at the area of the square times the needles in the circle divided by the needles in the square. If you try Buffon's experiment, you'll soon realize that the places where the needles land are not truly random. Moreover, even if you could drop them randomly, it would take a very large number of needles to get an approximation of pi as good as even the Bible's. Fortunately, computers can randomly drop simulated needles at a ferocious rate. Let's look at a program that does exactly that. We'll look at three functions. The first will throw some needles, or drop some needles if you prefer, in the vicinity of the square. The function throw needles simulates dropping the needles by first using random.random to get a pair of positive Cartesian coordinates, x and y values. It then uses the Pythagorean theorem, here, to compute the hypotenuse of the right triangle with base x and y. This is the distance from the tip of the needle from the origin. Since we know that the radius of a circle is 1, we know that the needle lies within the circle if and only if the distance from the origin is no greater than 1. We then use this fact to count the number of needles in the circle. The function getEst uses throw needles to find an estimate of pi by dropping num needles and averaging the result over num trials. It also computes the standard deviation, prints what it's doing, and then returns both the current estimate and the standard deviation. Now you might wonder why we're bothering with the standard deviation. And the answer is, we not only want an estimate of pi, we want to know how good the estimate really is. And that's what the next function does for us. The function estimate pi calls getEstimate with an ever-growing number of needles until getEstimate returns an estimate that, with a confidence interval, with a confidence of 95%, is within precision of the actual value. It does this by calling throw needles with an ever larger number of needles until the standard deviation of the results of num trials is no larger than precision divided by 2. Under the valid assumption that the errors are normally distributed, i.e. that random.random really is random, this ensures that 95% of the values lie within precision of the mean. All right, let's go run this and see what we get. So it starts off pretty quickly, generating some estimates of pi. But notice that I'm doubling the number of needles each time, which means it's going to double the amount of time required to get an estimate of each time. And so we can see that it's perceptibly slowing down. Rather than make you sit here and watch it, I've run this in advance. That's why I set random.seed to 0, so I'd know what results I was going to get, and transcribed it to a PowerPoint presentation. As one would expect, the standard deviations, this column, declined monotonically as we increased the number of samples. Would have been very discouraging if it hadn't. In the beginning, the estimates of pi also improved steadily. 3.148, 3.139, 3.141, 3.1414, getting better as we go. But it does not get monotonically better. For example, if we look at these two estimates, if we look at the estimate for 32,000 needles and 64,000 needles, we'll see that it actually got worse. This value is further from the actual value of pi than is this. However, if we look at the ranges defined by, say, one standard deviation around each of the means, both ranges contain the true value of pi, and the range associated with the larger sample is considerably smaller. Notice that this standard deviation is smaller than this one. So even though the estimate generated with 64,000 samples happens to be further from the actual value of pi, we should have more confidence in its accuracy. This is an extremely important notion. It is not sufficient. It is not sufficient to produce a good answer. We have to have a valid reason to be confident that in fact it really is a good answer. And when we drop a large enough number of needles, the smaller standard deviation gives us reason to believe that we do have a good answer. So we can go back here and see that the standard deviation is 0.002. And from that, we can conclude that this is a pretty good estimate of pi. In fact, it is a pretty good estimate of pi. I just lied to you. Having a small standard deviation doesn't mean we have a good estimate about pi. And in general, it doesn't mean that our program, whatever we're computing, is giving us a good estimate. All this means is that if we were to draw more samples from the same distribution, we can be reasonably confident that we would get a similar value. It says nothing about whether the value is actually close to pi. Before we can believe the results of any simulation, we need to have confidence in three things. One, that our conceptual model is correct. In this case, that when I did the algebra to compute the value of pi from the area, I'd done the right thing. That our implementation is correct. I could always have a bug in my code. It wouldn't be the first time. And finally, that we have enough samples to actually believe the result. That's the only one of these three that we learn by looking at the standard deviation. Let's see what happens if we get any of this wrong. I'll come back over to my code, and I'll come up here, and instead of using 4, I'll put in 2. Now we'll run it again. Just a little bug in my code. And you'll note I'm getting values that are nowhere as close to pi. My standard deviations are dropping quite quickly. And as I let this run, I'll get to some number of samples, probably about 500,000 again. And my program will claim it has computed a correct value of pi, but of course it hasn't. Whenever possible, one should attempt to validate results against reality. In this case, one should use some other means to compute an approximation to the area of a circle, for example, physical measurement, or pi, some physical measurement, and check that the computed value of pi is at least in the right ballpark.